In this video, I'm going to go over the Davenport diagram and then discuss how to interpret the acid-base disorders based on the value of the partial pressure of the carbon dioxide, based on the pH, as well as based on the concentration of the bicarbonate. And once done with that, I will go over different conditions that can disturb the acid-base balance in the body. Now, in order to understand the Davenport diagram, you will first have to know what's the balance between the CO2 and HCO3. So CO2 plus H2O will yield, via the carbonic anhydrase enzymes, the H2CO3. And then H2CO3 will dissociate into the H plus and bicarbonate. And so H plus is a strong acid while bicarbonate is a weak base. So this side of a reaction is acidic. And as we go away from this side of reaction, the reaction becomes basic. And now you may recall from the basic chemistry rules that if we increase the concentration of substrates, then the reaction will be pushed to the other side, while if we increase the products, then the reaction will be pushed back. So therefore, if we increase the concentration of the CO2 or decrease the concentration of the HCO3, then in that case the reaction will be pushed to the other side and become acidic. While if we increase the concentration of HCO3 or decrease the concentration of CO2, then the reaction will be pushed to the left sides and it becomes basic. Now the concentration of CO2 depends on the respiratory changes, while metabolic changes will determine the level of HCO3. So here we have the metabolic changes with regards to the concentration of HCO3. So therefore, if there is an increased absorption of HCO3, therefore we will have a metabolic alkalosis. While if we have a decreased concentration of HCO3, then we will have metabolic acidosis. On the other hand, if we have increased concentration of CO2 due to the decreased respiratory rate, then we will have a reaction pushed to the other side, so we will have respiratory acidosis. And if we have decreased CO2 from increased respiratory rate, then the reaction becomes basic, and that is a respiratory alkalosis. Now with this information in mind, let's go through the Davenport diagram and explain what we have here. Now in order to understand this diagram, we will first have to know the normal range for the pH, normal range for the partial pressure of the CO2, and then the normal concentration of the HCO3. So for pH, normal pH is between 7.35 to 7.45. So this is a normal pH range. For the PaCO3 or partial pressure of the carbon dioxide, it's between 35 to 45. And so the line shown in blue shows a normal range for PaCO2. And then for HCO3, it's about 22 to 28. And so therefore the lines that are shown here, the blue line for points A, B, and H, shows a normal range of the HCO3. And so if we have low level of HCO3 from this point on, therefore it will be a case of metabolic acidosis. While if we have high concentration of the carbon dioxides, then that would be case of a respiratory acidosis. If we have high concentration of HCO3, then that would be metabolic alkalosis. And then if we have a concentration of PaCO2 that is low, then that would be respiratory alkalosis. Now with that information in mind, let's try to determine the type of acid-base disorder that exists in any one of these points. So at point A, we have a normal pH. And so if we go above this pH, that would be, again, alkalosis. And if we go below 7.35, that would be acidosis. So here at point A, we have a normal pH. PaCO2 is in a normal range, and then the HCO3 is also in a normal range. So point A is neither an acidosis nor alkalosis. So this is a normal condition and normal balance between the CO2 and HCO3. And then here at point B, we will have alkalosis with respiratory alkalosis, but no changes in the HCO3. So therefore, point B is a pure respiratory alkalosis with a normal HCO3. Now, one other point that I would mention is that once there is a disturbance in the balance, like let's say that there is respiratory alkalosis, the body will try to get rid of some of the HCO3 to compensate for that alkalosis. So there are sometimes compensatory changes that will try to adjust the pH. But just know that the compensatory changes are never able to bring the pH back to normal unless there is actually a mixed acid-base disorder. So just keep that in mind. So point B, we have respiratory alkalosis with no compensatory changes. At point C, we have alkalosis with respiratory alkalosis as well as metabolic acidosis. So we can see that this respiratory alkalosis is the underlying cause of alkalosis. So here we have respiratory alkalosis with compensatory metabolic acidosis. So here the renal tubules are trying to correct for the original problem, which is from respiratory alkalosis, by getting rid of some of the bicarbonate. At point D, we have acidosis. So there is metabolic acidosis that is causing acidosis in this patient. But then on the other hand, the PaCO2 is in a normal range. So there is metabolic acidosis without any compensatory changes in the rate of the respiration. At point E, we have acidosis with metabolic acidosis, but then we also have respiratory alkalosis. So here, this condition is a metabolic acidosis with compensatory respiratory alkalosis. Now you may ask, why isn't it respiratory alkalosis with compensatory metabolic acidosis? Why isn't it the other way around? So the original problem is whatever that is matching with the pH changes. So here we have acidosis, and metabolic acidosis is the one that matches with it. So metabolic acidosis was the original problem, and then the body tries to compensate that by increasing the respiratory rate. So therefore, the diagnosis for point E would be metabolic acidosis with compensatory respiratory alkalosis. At point F, we have alkalosis. Again, it's in a normal range of PaCO2, but we have metabolic alkalosis. So here we have a metabolic alkalosis without any compensatory changes in the respiratory rate. At point G, we will have the alkalosis again, with metabolic alkalosis being the original cause of it, and then there is respiratory acidosis that is trying to compensate for that. So therefore, the diagnosis is metabolic alkalosis with the compensatory respiratory acidosis. With point H, we have the acidosis, and then it's the respiratory acidosis that matches that. So the original condition is respiratory acidosis, and then since the HCO3 is in a normal range, therefore there is no compensatory changes. So again, point H is just pure respiratory acidosis. Point I, we have the acidosis, and again, respiratory acidosis matches that. So we have respiratory acidosis with compensatory metabolic alkalosis. So again, the body is not respirating enough. There is accumulation of CO2 that causes respiratory acidosis, and then the renal tubules try to compensate for that by increasing the reabsorption of bicarbonate. So the diagnosis for the point I would be respiratory acidosis with compensatory metabolic alkalosis. And that was the whole discussion for the Davenport diagram. Now there is another way that you may be asked on the exam, and you may not be given the Davenport diagram, and it's the same concept. You will have to know the normal range for pH, HCO3, and PCO2, and then based on that, you can determine the acid-base disorder that exists there. So now let's go through some of these examples. I won't fill in the whole table, but let's do a few examples together just to get ready for that. So let's say this point, for instance, we have a normal pH. There is increased level of HCO3. So therefore here we have metabolic alkalosis. And then we also have high level of the CO2. So therefore we also have respiratory acidosis. Now here, let's look at the pH. Does it match the metabolic alkalosis or respiratory acidosis? And the answer is it matches neither. It's right in between the two. So for this condition, we have a mixed metabolic alkalosis with respiratory acidosis. So I just discussed earlier that if we have an acid-base disturbance, the compensatory changes tries to correct for that, but never gets in a normal pH range. So if we do get in a normal pH range, then it means that it's a mixed acid-base disorder. So in this case, we have mixed metabolic alkalosis with respiratory acidosis. On the other hand, in this example, we have mixed respiratory alkalosis, so now the CO2 is low, and then the HCO3 is also low. So therefore we have mixed respiratory alkalosis with metabolic acidosis. And then let's do a few more examples together. So for this example here, we have a high pH, so we have alkalosis. And then the HCO3 is low, so therefore we are having metabolic acidosis. And then the PCO2 is also low, which is for the respiratory alkalosis. So in this condition, it's the respiratory alkalosis that causes the pH to be higher than normal. So we have respiratory alkalosis with the compensatory metabolic acidosis. And then the final example we are going to do here we are having again high pH. So again we are having alkalosis that is going on. The HCO3 is higher than normal, so we have metabolic alkalosis. And then the PCO2 is in a normal range. So therefore here we are having a pure metabolic alkalosis with no compensatory changes. And so you get the hang of it after doing some examples on how to interpret the acid-base disorders. Now there are also conditions that will disturb the acid-base switch you will have to be familiar with. So here we have the equation for anion gap. An anion gap helps you to determine the type of metabolic acidosis that we are having. So if the anion gap is higher than the 8 to 12 normal range and there is metabolic acidosis, then usually one of these causes that I've listed in this box is the underlying cause of metabolic acidosis, because these conditions increase the level of the acid. So for instance, like aspirin or lactic acidosis or diabetic ketoacidosis. So the level of acid keeps increasing, as a consequence of which there would be elevated anion gap that is causing the metabolic acidosis. Now the equation for this anion gap is the concentration of serum for sodium minus the level of HCO3 minus the level of chloride. So let's say for instance that we have serum concentration for sodium of 140, bicarbonate of 20, and chloride of let's say 90. So therefore the anion gap for this patient would be 30. And 30 is higher than the normal range, so therefore if there is a metabolic acidosis in this patient, then one of these causes could be the cause of metabolic acidosis, like for instance diabetic ketoacidosis, ingestion of the ethylene glycol, paraldehyde, methanol, iron, uremia, or use of the salicylates, like for instance aspirin. Now regarding aspirin, you should know that there is initially the medullary stimulation, as a consequence of which it will increase the respiratory rate, and thus it will initially cause respiratory alkalosis. But then later on, since it causes like acidic changes, it will lead to the metabolic acidosis with elevated anion gap. So just keep that in mind. With aspirin, there would be initially respiratory alkalosis, but then later on they develop metabolic acidosis with elevated anion gap. Now, regarding the changes that I've listed in this box for you, there is a memory aid called Impulse, or the other memory aid that is available is called Modpiles, which summarizes all these changes. Like for instance, I for iron, M for methanol, P for paraldehyde, U for uremia, L for lactic acidosis, S for salicylates like aspirin, E for ethylene glycol, and finally D for diabetic ketoacidosis. Now you should also note that diarrhea also causes metabolic acidosis, but you've noticed that diarrhea wasn't listed among the conditions that I've listed in this box, and the reason for that is that the metabolic acidosis that is caused by diarrhea has a normal anion gap. So diarrhea also causes metabolic acidosis with normal anion gap. And the reason for that is that diarrhea causes loss of bicarbonate inside the stools, as a consequence of which there would be metabolic acidosis. But since there is no increase in the level of the acids, therefore the anion gap would be normal. And then there are also other conditions that cause metabolic alkalosis which you need to be familiar with, and these include, for instance, vomiting, where the patient is losing the gastric acid in the vomitus, and the use of a diuretics, like for instance furosemide, or hydrochlorothiazide, which causes loss of the H plus in the urine, again leads to the metabolic alkalosis. So the memory aid that I have for you is that anything that comes from the front, like for instance diuretics or vomiting, cause metabolic alkalosis, while anything that comes from the back leads to the metabolic acidosis. And then keep that in mind. Here we have a normal anion gap, while with the memory aid of impulse or mud piles there would be also metabolic acidosis, but then there would be elevated anion gap. And that concludes the discussion of the acid-base disorders.